Hey 10th graders. So we've been talking a lot lately about pressure, volume, temperature, number of moles of a gas, and how all those things are related. You acted it out outside in a balloon, and you've been thinking about the relationships between all of those variables since then. You also know that Ms. Lauerman and I need your advice for our scuba diving trip to see what equipment we need to bring. So you're going to use these relationships between pressure, volume, temperature, and number of particles of a gas now mathematically and see how they're related to each other, and we're going to do some calculations. So here's the title of your notes, Solving Gas Laws Problems. You should copy this down and write down all the other underlined material in this PowerPoint. So here we go.
So from class and from your first video, you guys already know that we have two different equations that we use for gas laws. Okay, so one of them is P1V1 over T1 equals P2V2 over T2. All right, and this is the equation that we're going to use if we're changing the conditions in the problem. Okay, so some variable in the problem is changing during the course of the problem. All right, so what happens is if you change any one of these variables, all of the other variables are going to change as well. Okay, so sometimes one variable will be held constant, meaning it won't be changed. Okay, and in that case, we can actually just cross that variable out, and we're going to look and see how we can do that now.
So let's look at an example. Let's say that we hold temperature constant. That means temperature is not going to change. Since we don't even need to put any numbers for temperature into our equation, we can just cross it out. So we're just left with P1 times V1 equals P2 times V2. So how are these related? You know from your experiment out in the balloon that if you increase the pressure, the volume is going to decrease. They have an inverse relationship. And the opposite is also true. If you decrease the pressure, the volume will also increase. So let's look at a sample problem. You probably want to write down this problem. So hit pause, copy this down into your notebook. At the Earth's surface, the volume of a balloon is 2 liters. If temperature remains constant, calculate the new volume of the balloon if it's submerged underwater 100 feet, where there's a pressure of about 4 atmospheres. So we have this balloon, 2 liters, I don't know, about this big, you think? So it's at Earth's surface. We're going to bring it down 100 feet underwater with us, where there's a pressure of 4 atmospheres. This is the pressure pushing on the outside of the balloon, and I would expect that the balloon would get crushed into a smaller volume. So I'm thinking that the new volume has to be smaller than the original volume. So here's how it works. We're not changing temperature. The problem says nothing about temperature. We're going to cross it off and write down our new relationship. You should copy this down into your notes as we work through it. And I know that the pressure at Earth's surface is 1 atmosphere. That's a good thing to just know and memorize. So I'm going to plug in all of the numbers that I do know. So the original pressure, P1, is 1 atmosphere. The original volume, V1, is 2 liters. The new pressure, so at the end of the problem, the pressure has changed to 4 atmospheres, and we don't know what V2 is. That's what we want to solve for. I multiplied 1 times 2 on the left, and I left the right-hand side the same. And then I divided both sides by 4, so that we get V2, the new volume, is 0.5 liters. So the new volume of your balloon, it started out at about 2 liters, and it's about half a liter when we're done changing it. So the volume will decrease to half a liter.
All right, so now you've seen that if temperature is held constant, we can just cross out temperature. Okay, and the same thing happens if pressure is held constant. Okay, so if the pressure isn't changing over the course of the problem. All right, so what we can do is just cross out pressure on both sides of the equation if it's being held constant. All right, so basically what that means is that if we increase the volume, the temperature is going to go up. Also, if we decrease the volume, the temperature is going to go down. Okay, so without pressure, we can just look at the relationship between volume and temperature. All right, so for example, let's say we had the problem you guys see here. So a balloon at room temperature, which is about 20 degrees Celsius, has a volume of 2 liters. The balloon is gently heated until the gas inside it is 80 degrees Celsius. If pressure stays constant, you need to calculate the new volume of the balloon. All right, so we're starting with a balloon about 2 liters at 20 degrees Celsius at room temperature, and we're heating it up. All right, and we know that if pressure stays constant, as the temperature increases, the volume is going to increase as well. All right, so we're expecting that the balloon is going to get bigger as we heat up the balloon. All right, so let's see if that actually happens in real life. All right, so we've crossed out our pressures. We're just looking at volume and temperature. So the first thing we have to do is to take these values in degrees Celsius and convert them to Kelvin. So we warned you guys yesterday that we were going to do this to you. All right, but you guys are pros now at converting between Celsius and Kelvin, so this is going to be no problem at all. All right, so all we need to do is to take our temperatures in Celsius, like 20 degrees Celsius, and add 273. Okay, so that gives us 293 Kelvin for our first temperature. And our second temperature is 80 degrees Celsius, so again, we just add 273 and we get 353 Kelvin. All right, so we're tricky, but we're not too tricky. I think you guys can all handle this. So now we're going to take these values that we have from our problem and we're going to plug them in for the volume and temperature in our problem. All right, so originally our balloon has a volume of 2 liters and a temperature of 293 Kelvin. All right, so those are going to go in for V1 and T1 on the left side. At the end of the problem, our temperature is 80 degrees Celsius and we don't know what our volume is. All right, so we put 353 Kelvin in for our second temperature, and we don't know what V2 is. That's what we're trying to solve for. All right, so as you guys are writing this down in your notes, you'll see that we solved for the left side first. So we divided 2 liters by 293 Kelvin and got 0.0068. Then we multiplied both sides by 353 to find out that our new volume is 2.4 liters. Now you guys are welcome to solve this by cross-multiplying as well. Whatever works best for you is what you should do.
Hey, look, the volume went up. Yeah.
Excellent. Exactly. All right. So our balloon got bigger when we heated it up.
I like to check my work just by making sure the answer makes sense. If the volume had gotten smaller, I would have known that I made a mistake. So volume goes up, I feel pretty good. Temperature goes up, volume goes up. Awesome. So one more example problem of this type to relate pressure and temperature. So here's the entire equation that you have written down. If we hold volume constant, so we're going to cross it out, it's not going to change. Let's see how pressure and temperature relate to each other. If we increase pressure, temperature will also increase. Or if we decrease pressure, the temperature will decrease. So they're related in the same way. One goes down, the other one goes down. So let's use this to solve a problem. And we're going to do a can of hairspray problem. You'll probably see these pretty often in this class. A can of hairspray has an internal pressure of 2 atmospheres at room temperature. The can is placed near the heater. They tell you not to do that, and we did it in this problem. And the temperature increases to 50 degrees Celsius. What is the new pressure inside the can if the volume of the can stays constant? So you have this can, the volume can't change. It's not like a balloon. So what's going to happen to the pressure inside the can? So we're not dealing with volume at all. It's staying the same. So here is the equation we're going to use after we cross off volume. And we, once again, need to convert Celsius to Kelvin. So room temperature, 20 degrees Celsius plus 273 gives us 293 Kelvin. And the new temperature, 50 degrees Celsius plus 273 gives us 323 Kelvin. So that takes care of that Kelvin problem right away. And we're just going to plug in. The original pressure is 2 atmospheres. The original temperature is 293. The new pressure we don't know, so we're just going to leave P2 in the problem. And then the final temperature is 323 Kelvin. So we're going to solve on the left-hand side and then multiply both sides by 323. And our new pressure is 2.2 atmospheres. So let's just do a check to see if this sounds right. Our temperature went up, so we expect the pressure in the can to go up because those particles are moving around faster and bouncing off each other and off the walls of the can more frequently. So the pressure goes up. I feel good about that answer.
All right, so now, just like we always do, you're going to write a 2 to 3 sentence summary of what you learned in the video. What was the whole point of what we just taught you? All right, and then you're going to write down any questions that you still have that you're unsure about, and we'll answer them in class tomorrow. Thanks for watching.
All right, see you later.